A single point ground, also known as a star ground, connects all ground points in a circuit or system to a single reference point. This reference point is commonly referred to as the star point. The primary advantage of a single point ground is that it provides a central point for all current to return, significantly reducing the occurrence of ground loops and minimizing electrical noise. By simplifying the grounding scheme, a single point ground reduces the likelihood of electromagnetic interference, or EMI. This makes it particularly suitable for sensitive electronic systems where minimizing noise is crucial. In contrast, a multi-point ground connects ground points to multiple reference points or chassis points throughout the system. While a multi-point ground can be used in situations where establishing a single reference point is impractical or impossible, it introduces potential challenges. If not properly designed, a multi-point ground can lead to ground loops and increase electromagnetic interference. The feature comparison between these two grounding methods can be broken down by four aspects. Firstly, the central grounding point is present in a single point ground system through the star point, whereas it is absent in a multi-point ground. Secondly, ground loops are reduced in a single point ground setup, but pose a potential concern in multi-point grounding. Thirdly, electromagnetic interference is minimized with single point grounding but can increase with multi-point grounding if the design is inadequate. Fourthly, in terms of simplicity, a single point ground scheme is simpler, while a multi-point ground scheme is more complex. Finally, a single point ground is typically used in low noise or sensitive systems. Multi-point grounds may be necessary for systems that have multiple ground references. Ground loops occur when there are multiple paths to ground, creating unwanted current flow. This can lead to voltage differences between different ground points, which can introduce noise into sensitive circuits. Electromagnetic interference is a disturbance caused by electromagnetic radiation emitted from various sources. This interference can disrupt the normal operation of electronic devices. Single-point grounding minimizes electromagnetic interference by ensuring that all ground currents flow to a single point, preventing them from circulating through the system and radiating electromagnetic energy. When deciding between single-point and multi-point grounding, consider the sensitivity of the equipment and the complexity of the system. Single-point grounding is generally preferred for sensitive equipment and simple systems, while multi-point grounding may be necessary for complex systems where a single ground point is not feasible. In cases where multi-point grounding is necessary, careful design and implementation are crucial to minimize ground loops and electromagnetic interference. This may involve using shielded cables, filters, and other techniques to reduce noise. It is also important to ensure that all ground connections are properly made and that the grounding system is properly tested to ensure that it is functioning correctly. The National Electrical Code, or NEC, provides guidelines for grounding electrical systems. Although the specific requirements may vary depending on the application, the general principles of grounding remain the same. Understanding these principles is essential for ensuring the safety and reliability of electrical systems. Grounding serves three primary purposes. Firstly, it provides a low impedance path for fault currents to return to the source, allowing overcurrent protective devices to trip and clear the fault. Secondly, it minimizes the voltage between electrical equipment and ground, reducing the risk of electric shock. Thirdly, it provides a stable reference point for electronic circuits, reducing noise and improving performance. The single-point grounding method connects all ground wires to a single, central grounding point. This point is then connected to the earth ground. This method helps to prevent ground loops which can cause noise and interference in electronic circuits. The multi-point grounding method connects ground wires to multiple grounding points throughout the system. This method can be used in large systems where it is not practical to run all ground wires back to a single point. However, multi-point grounding can increase the risk of ground loops. Choosing the right grounding method depends on the specific application and the potential for ground loops and noise. In general, single-point grounding is preferred for sensitive electronic equipment, while multi-point grounding may be necessary for large systems. Regardless of the method chosen, it is important to ensure that all ground connections are properly made and that the grounding system is properly tested. A ground loop is a closed circuit formed by grounding connections. Ground loops can cause noise and interference in electronic circuits. They occur when there are multiple paths for current to flow to ground. This can happen when two or more pieces of equipment are grounded to different points in the electrical system. The difference in potential between these 2 points can cause current to flow through the ground loop, which can introduce noise into the circuit. Ground loops can be prevented by using single-point grounding. With single-point grounding, all ground wires are connected to a single, central grounding point. This eliminates the possibility of multiple paths for current to flow to ground. Another way to prevent ground loops is to use isolation transformers. Isolation transformers isolate the equipment from the electrical system, which prevents current from flowing through the ground loop. Electromagnetic interference, or EMI, is a disturbance that can affect the performance of electronic equipment. It can be caused by a variety of sources, including radio waves, microwave radiation, and electrical noise. EMI can cause electronic equipment to malfunction or even fail. Grounding can help to reduce EMI by providing a path for the interfering signals to ground. This helps to prevent the signals from interfering with the operation of the equipment. Shielding can also be used to reduce EMI. Shielding involves enclosing the equipment in a conductive material, such as metal. This helps to block the interfering signals from reaching the equipment. Filters can also be used to reduce EMI. Filters are electronic circuits that are designed to block certain frequencies of electromagnetic radiation. They can be used to filter out the interfering signals before they reach the equipment. The National Electrical Code, or NEC, is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC covers a wide range of topics, including grounding, wiring methods, overcurrent protection, and equipment installation. The NEC is updated every 3 years. The latest edition of the NEC is the 2008 edition. The NEC is adopted by most states and local jurisdictions in the United States. Compliance with the NEC is required by law in most areas. The NEC is a complex document, but it is essential for anyone who works with electricity. Understanding the NEC can help to ensure the safety of electrical installations. The NEC covers grounding requirements in Article 250. Article 250 provides requirements for grounding and bonding electrical systems. It covers topics such as grounding electrodes, grounding conductors, bonding jumpers, and equipment grounding. Article 250 also provides requirements for grounding sensitive electronic equipment. These requirements are designed to protect sensitive equipment from damage caused by voltage surges and other electrical disturbances. Grounding electrodes are used to connect the electrical system to the earth. The grounding electrode system must be properly sized and installed to provide a low impedance path for fault currents to return to the source. Grounding conductors are used to connect the equipment grounding conductor to the grounding electrode. The grounding conductor must be properly sized and installed to provide a low impedance path for fault currents to return to the source. Bonding jumpers are used to connect metal parts of the electrical system together. Bonding jumpers must be properly sized and installed to provide a low impedance path for fault currents to return to the source. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. Equipment grounding conductors must be properly sized and installed to provide a low impedance path for fault currents to return to the source. In summary, the grounding selection between a single or multi-point option is based on its system design.